Hello and welcome to my presentation, and thanks George for inviting me here. Today what I will present is a straightforward extension of a well-known diffusion model to account for network effects which are of substantial importance in today's digital economy. And what we will see is that this simple extension that we do leads to a critical mass phenomenon, meaning that we need a certain amount of sales in order for a product to be successful. And furthermore, we consider the impact of a budget constraint, and this will we will also see that it leads to methodologically interesting results, because what we will see is that the optimal solution in this case can be abnormal. It's a joint work with Gustav, Dieter, Richard, and Peter. And yeah, I will start out by giving a short introduction. Then I will present the problem without budget constraint. Then I will discuss the impact of the budget constraint before I will conclude. So in today's digital economy, there is this phenomenon, so to say, that products get more valuable the more people use them. These are the so-called network effects. And just think about the software that we're using just now. If you're the only person in the world who uses Zoom, it's of little use for you. But if all people that you know use Zoom, it's really attractive for you. It's you even are pressured into using it because it's the way that you want to communicate with your peers. It's the most simple thing to do. And similar holds true for other communication software like WhatsApp, Signal, Telegram, and whatever. Network effects also occur in social media platforms. The more people use Facebook, the more you can share your news with your friends. The more you can share your pictures of your cat or your dog or whatever on Instagram, the more people use it. But there's also this platform aspect to it. So if you consider, for example, YouTube, the more people use YouTube, the more attractive it gets for content providers to upload new content. And the more content you have on YouTube, in turn, makes it more interesting for more people to use it. Then network effects can also play an important role for smart products. For example, for autonomously driving cars, you have the more people use this autonomously driving cars, the better the cars can coordinate and the better they are at avoiding traffic jams. Also, when you consider, for example, software like YouTube, the products often have some preference learning algorithm included. And the more people use YouTube, the more they learn about your preferences with respect to videos. So the more people use this algorithm, the better it can get at predicting on what people like to see and what not to see. And this makes in turn the software also more valuable. In previous models that we're basing our paper on, you had different effects included, like word of mouth effects and market saturation, and we will extend in particular Gold's second diffusion model to account for account for these network effects that play an important role in today's economy. So network effects means that the product is not attractive when only few users use it. So it's more difficult to attract additional customers when you only have few customers. But when you have a lot of customers, it's quite easy, because then you have this kind of self-enforcing effect. People pressure other people into using a certain software to communicate with them, for example. And what is also seen in practice is that a critical mass of users is necessary for the success of a product. For example, when you take, for example, Amazon Marketplace, Amazon started out selling books, and they offered a wide variety of books and at a cheap price. And in this way, they grew. But in the beginning, there were no real network effects. Word of mouth effects, of course, played a role in Amazon getting popularity, but only when it, Amazon was launched around 95, and in 2000 it opened up its platform for other firms to sell their products. So this had also this kind of network effects, which made Amazon more attractive. So these additional sellers made the product, the Amazon, more attractive for the customers because they could buy more items there. But on the other hand, because of this large number of users that Amazon already had, it was very attractive for sellers to also participate in this marketplace, to be able and sell their goods. And yeah, and the more sellers and the more customers. So here you have again this network effect in this platform. And also for Facebook, you can see when you observe the history of Facebook started out at colleges and was very specific, offered specific their platform for students. And only after some time, when there were enough users, they opened up for the broad public. An example for failure for a product which did not achieve too many users and became unsuccessful in the long run was Windows Phone. It was a good platform for mobile phones, but it never had so many users that it was, and because it did not have so many users, it was not attractive for app developers to develop software for Windows Phone. So for example, there was no Instagram on Windows Phone, there was no Pokemon Go on Windows Phone. And so because of this lack of availability of some software, it was not so attractive for people to use it. And yeah, people left for other platforms that had already more users and were therefore more attractive for the software providers. And yeah, the Windows Phone numbers were never really that high, but they declined then over time. So for Windows Phone, a critical mass that led to the success of the product was never achieved, and yeah, now it's practically gone. In principle, what you could do is you could advertise to attract customers, but as already indicated, it's quite difficult to do when the number of users is small. And therefore, it's when a user is small, then you need a lot of money, but usually you have a limited budgeted you have a limited budget, and this makes things more difficult. But yeah, at first to consider okay. But what we will see later on is that the introduction of a budget constraint leads to an abnormal optimal solution, which plays a role for the actual solution. And abnormal in optimal control problems means that the objective is ignored to determine the optimal control. So you have in the Hamiltonian this multiplier lambda 0, which is in normal problems set to 1 without any loss of generality. But in abnormal problems, it needs to be set to 0. And we will see that here in this simple marketing model, we get an abnormal solution. Yeah, normality is something that can be guaranteed for a certain class of optimal control problems, namely when the time horizon is finite and the end state is free, but it cannot be guaranteed for infinite time horizon problems with a free end state. In the past, there was this abnormality. When you thought about abnormality, you usually always came to this example by Halkin, who was the first one who dealt with this phenomenon. And yeah, there you would have a solution, an abnormal solution, when you started with an initial value of 0. This initial solution would lead to an objective value of 0. And if you just deviate, if the initial state would just deviate a little from this value, the objective would immediately get minus infinity. And yeah, just as I said, if starting at exactly the origin, the solution was abnormal. But there is, for this Halking example, there's no real good economic interpretation. We tried hard to find one, but there isn't, or at least we haven't found one so far. And so in the past, abnormal problems were considered that there is something wrong with the model formulation, and it is not relevant for real application. And here with the present model, we will illustrate that this is not true. Okay, but let's get now to the actual model. And first we start with the model without budget constraint. Yeah, so X is the sales level, it's our state variable. U denotes the advertising expenditures, and we just have a few parameters, are as usual, the discount rate. We have some advertising efficiency, and we have some depreciation or forgetting rate of the sales level, which is denoted by delta. And G of X is our diffusion term. And here on the present slide, you can see the state equation. So yeah, and in comparison, and you also see how this diffusion function looked like in past models. So in the Vidal-Wolf model, you just had this linear function. You had just 1 minus X. You can see it here. The higher your sales level, the more difficult it gets to attract additional users because of market saturation. In the gold model, you had this term X times 1 minus X, yeah, which you can see here. In the beginning, it is very difficult to attract customers, but the change in the advertising efficiency with respect to customers is large when you have a small number of users. So it's more of, yeah, advertising is difficult, but additional users help you a lot there. And our model is a straightforward extension of the second gold diffusion model by Gold. We have here the term X squared times 1 minus X. The interpretation of that is, yeah, 1 minus X is the fraction of people who don't use a product. So we could also consider it to be yeah, the fraction of potential customers, and X is the fraction of users. So the probability that a use of a product meets a person who does not use the product yet is X times 1 minus X. And we assume that the probability that this encounter leads to the adoption of the product, we assume that this increases with the number of users X. So yeah, this term X squared 1 minus X gives you the rate at which people are convinced to use a product related to yeah, and we multiply this with some term accounting the efficiency of advertising. So we have U is the advertising spendings, and we have here the square root of U, which we use because we assume that yeah, you cannot, we have a declining advertising efficiency. So the more you advertise it, yeah, the less efficient your measures get. Yeah, so this term here describes yeah, the impact. It describes how difficult it is. It describes how many, how you increase the sales rate, and this term, the second terms, gives you the depreciation of the sales rate. So people forget about your product, and this is what this term is about. And yeah, last but not least, you have the yeah, last diffusion term that we compare it is the one by Seidl, which we has this square root term, and you can also see here that the advertising that it gets more and more difficult to attract new customers the more people use it. In comparison to the Wolf model here, the decline is not so, it's less steep in the beginning, but it gets steeper. So more and more difficult the more users you already have. And yeah, for our model, you can see here, if you compare this curve in the beginning, it's very difficult to attract customers. An additional user helps you a little bit, but not that much. Really, only once you obtain a certain amount of customers, it gets easier and easier to attract customers. And then if the number of users is already large, you have this market saturation effect. Okay, and then yeah, here, yeah.
Yes, so in this, the network model, I see that even if there is like a, I mean, there is no critical mass phenomena here, right? Because even if I increase by a slightly X, the increase in X dot is very high, right? I mean, if you see the gold model, the increase is not high. it's decreasing. But for network model, there is a positive tangent, right, in some way.
Mhm.
So the x
So
double dot will be very high in this case.
yes, exactly.
No?
So
Okay.
well, no. I mean, if I'm not completely sure about the question, but I will get to this critical mass phenomenon. I hope this gets clear. Effectively, what it means is yeah, this x dot, this term is very small when the number of users is small, and yeah, larger for an intermediate value of the users.
Okay.
And yeah, it means that here in this area that advertising is very inefficient and very difficult. And yeah, I will show you this then in the phase portrait. So I hope this gets more clear how the impact of that is. And you can see then here the complete model. Yeah, we have yeah, we want to maximize our revenues. We have here the advertising costs. Yeah, here again, this inverse demand function. And yeah, we assume that our decision maker has time preferences. Yeah, so the time horizon is assumed to be infinite. And yeah, the state equation, I talked about that. We have non-negativity conditions, but we do not need to consider them in more detail because they do not get active anyways. So yeah, so then what we do is, as usual, we use Pontryagin's maximum principle. For that, we use the Hamiltonian. And yeah, here you can see this Lagrange multiplier, which will play a big role later on when we get to the problem with budget constraint. It's, yeah, in a normal problem, it's 1, and in an abnormal problem, it's 0. Yeah, and yeah, the lambda here is the usual costate. And yeah, we apply Pontryagin's maximum principle, derive the first order necessary optimality conditions, and from that we get an expression for the optimal advertising expenditures. Yeah, so what we see here is, yeah, the more valuable a product it gets, the more I would advertise. The more efficient advertising gets, the more I would advertise. And then as we are dealing with infinite time horizon, we have a look at the long run solution, at the long run steady states, and we can find one steady state for this problem analytically. It's one where the state variable is 0, and yeah, the control here is at its bound. It's also 0, and yeah, it's when we consider the eigenvalues, we see it's a saddle point. There are more steady states in this problem, but they have to be calculated numerically. So yeah, so let's go to the numerical results. As usual, we do a lot of things numerically. And these are just the base case parameters. And what we see is that our long run outcome depends on the parameter values. So here we considered in particular how myopic or farsighted our decision maker is, the time preference rate R, and the forgetting rate. So how fast do customers forget about the product delta. And we see that there are essentially 3 long run outcomes. The first one is Skiba, is what we call the Skiba scenario. What we have in this scenario is that the long run solution is history dependent, and which means that which steady state we approach in the long run depends on the initial state value. And what we have in this scenario is an indifference threshold point at which the decision maker obtains the same objective value for approaching different steady states. So, and therefore is indifference between the different options. Then we have what we call the weak Skiba scenario. There, the solution is also history dependent. We also have a threshold point, but there is not this indifference property. So if you start directly on this threshold point, you stay put there. If you start to the left, you go to the 0 steady state. If you start to the right, to a higher steady state. And what can also happen is that you have a unique solution. There you just go to the 0 steady state, and I will illustrate you the different cases then. So the most interesting case here is the Skiba scenario. So this is our base case. It occurs for the parameters that I just described here. And what happens here is we have two steady states, one at 0 and one interior steady state with a relatively high level of customers. When we consider here the x dot isocline, we see that this is U-shaped, and what it means is, what it implies is that we well, it separates the areas in the state space for which we can we can find a feasible, for which we can use our control to increase the state, and an area in the state space for which our sales level is always certain to fall. So either because it's too expensive, or well, in this case, it's not just here. If we're below this x dot isocline, we cannot increase the state value. So this isocline gives us the minimum level of the control that we need to be able to increase our sales level. And yeah, what we can see here is that if the initial state value is very small, we don't put much efforts into marketing. We just let the state value decline. We just make a little bit use of the small number of users we have. And yeah, and on the long run, we are bound to fail. If the number of users is larger, then advertising pays off to a certain extent. You can see here, because of this U-shaped form of this isocline, the smaller the initial number of users is, the more I have to invest into advertising and to be able to increase the number of users here. So you can see here, I mean, I cut off the figure to be able to show what's happening down there. But if you would continue this figure, you would see that both this stable manifold, the path that leads to the high steady state, it goes still up here and to the left. And yeah, so when you're here, you when the number of users is small, you would need quite a lot of efforts to be able to increase the number of users. And what happens then is, yeah, the more efforts you need to be able to increase the number of users, the more costly it gets and the less profits you make. And at a certain point, which is the Skiba point, X bar, the solution that you obtain for the solution path that you obtain for approaching the high steady state delivers the same objective value as the solution path for approaching the low steady state. And this is something that you can see here in this graph. And so at this point, X bar, the decision maker's indifference between approaching the high steady state and the low steady state. Yeah, on the left, it's better to approach the lower steady state. It doesn't pay off to invest too much to go to the high steady state. On the right side, it pays off to approach the high steady state. Yeah, but what you can see here in this, what in this context is also very interesting, is the co-state variable. And you can see here that here in vicinity of the Skiba point, those co-state variables also get enormously large. And this is because of the network effect. Here, it would really pay off to have additional users who could help you in attracting other customers. So this explains why the co-state goes so high into the, yeah, becomes so high here. Here, it just really would help you a lot if you would have more customers. And yeah. Okay, so here you can see here that the solution is history dependent, and here you have then so to say a critical mass. I mean, here it's in principle, if the number here in this case, in principle, it would be still possible to reach the high steady state, but it does not pay off because it's so expensive because of this network effect. Okay, and yeah, here you can see the time paths for the different solutions that you obtain when you start exactly on the Skiba point. So yeah, this is the solution here on the left-hand side for approaching the high steady state. You can see here this classical S-shaped adoption curves in the beginning, because the product is not very attractive to be used. The spreading of the product goes very slowly. Very high advertising efforts are necessary to be able to increase the number of users. And then at a certain point, you have this kind of self-enforcing effect. The product gets more and more attractive, more and more people start to use it. You can see here that adoption here happens pretty fast. Then, yeah, and then after some time, because then it's more and more difficult to find additional users, this increase in attracting customers gets slower, and then in the long run you approach a steady state with a relatively high number of customers. And yeah, the other way, the other potential strategy is to approach the lower steady state. He would put in some marketing, some advertising efforts to slow down the decrease of the sales level. And yeah, but here you would not do much, because yeah, the number of users is small. It does not pay off. Increasing the number of users would be too costly in this case here. Okay. The second kind of outcome that can occur here is this weak Skiba scenario, where the solution is history dependent, but we do not have the threshold. We do not have this indifference property of the threshold point, and this can happen if either R or delta are very low. So here I illustrate that for this higher, or I mean, actually it's the intermediate discount rate, because if R is very large, then you get into an area where approaching where you have a unique optimal solution is optimal. So here you have this intermediate solution for intermediate values of R. So what happens? A higher value of R means that the decision maker is more myopic to before, and puts a stronger emphasis on making immediate profits. And this makes advertising less attractive, which in turn means that the higher steady state will move to the left. What happens is that you have an intermediate steady state, which is unstable. This steady state, the higher the discount rate R, the more it moves to the right, because I mean, effectively you have less incentive to advertise. And this in turn means that you would approach the lower steady state for a larger for larger values of the for large initial state values. And what happens here is then in this case, because you have this threshold, this area in which you would approach the lower steady state, which becomes larger because you wouldn't want to make do too many advertising efforts so that you can actually approach the higher steady state. What happens then is, what you can see here is that the difference between approaching the higher and the lower steady state is not as big as what you had before, and this will play a role also later on when it comes to abnormal and normal solutions. But anyways, yeah, so what you have here is then you do not have this indifference property of the steady state, which is due to the fact that this threshold that now for larger areas in the state space, it's attractive to go to the lower steady state because you don't want to spend too much on advertising and waste your profits in this manner. Yeah, because of that, you make less profits, and because of that, this threshold moves to the right. And when it moves to the right, well, long story short, you lose this indifference property. And if R is even larger, or also what happens if your forgetting rate is very large, so people do not stay too interested in your product for a long time, then you just have a unique solution. So this is the most uninteresting case. You just would approach the zero steady state no matter where you start at. In the beginning, if the number of users is very large, you would not do much advertising, because then it's difficult to, because of this market saturation effect, it's difficult to attract customers, to keep them put, to reach customers. So here you would not do much, but here if the for an intermediate value of the sales level, you would do some advertising because it's most efficient there, and it would slow down the depreciation of your sales. And so here you would collect also some revenues from the existing users that you have, but on the long run, it's too expensive to advertise in a manner that you have a high level of customers in the long run. Okay. So this is the problem without budget constraint. As you could see, we had 3 different outcomes depending on the parameter values. And what we had a look at then is what happens if you have a budget constraint. Because if you have a budget constraint, because I mean, our thought was, okay, if you have, in principle, you could approach a higher steady state. It just does not pay off to do that. But sometimes you have a budget constraint, and this makes it even harder when there is this network effects. And we wanted to see what happens in this case. And so the problem is the same as what we had before, but now we have an additional constraint on the control on the advertising spendings, namely that it must be smaller or equal to some budget value B. And then, we have to look, of course, at the Lagrangian. We include here the constraint. We have this Lagrange multiplier, where we have, and we have this complementary slackness condition, which needs to hold, which you can see here. And what is important here in the present context is that this a solution at the boundary is only feasible if the Lagrange multiplier is larger or equal to 0. The Lagrange multiplier here, so we apply again Pontryagin's maximum principle, set the first order derivative of the Lagrangian with respect to the control equal to 0 and solve for the control. We have 2 possibilities how the control might look like. So either it's in the interior of the feasible region, if then the optimal control assumes the same expression as what we had before this value, or it is equal to B, if this condition, so if this expression would be larger or equal to B, this is not feasible, but it would be this. And if the control is at the upper bound, we have some conditions on the Lagrange multiplier, which follows from the first order necessary optimality condition. And what needs to hold true is that this expression needs to be larger or equal to 0. Okay, and then what we can do then, the next step is again to look at the steady states. And what we find here is that we have 2 steady states. In principle, there are 2 steady states at the bound possible. One smaller one, this is xb1, and one larger one. So this is this expression which we can easily derive by having a look at the at x dot, setting it to 0, and at the budget, and then having a look at the budget constraint. So what I want to introduce now is the concept of a stalling equilibrium, because what we will see is that xb1 is a stalling equilibrium, and what we call stalling equilibrium is a steady state for which it holds true that the state equation obviously needs to be equal to 0. So this is a steady state property, and what makes this steady state peculiar is that for all feasible values of the control, x dot is strictly smaller than 0 if the state value is smaller than the steady state in vicinity of this stalling equilibrium. So I will show you what I mean by that. So let's see here, you have the x dot isocline. So U bar is just like what we had before, the minimum level of the control that you need to be able to increase the control. And then you have the budget constraint. And what you can see here is, you have 2 intersections, 2 steady states, and xb one, the lower steady state, and the larger steady state. And when we consider then here this picture, just as said, U bar is the minimum level of the control that we need to be able to increase the state value. And when we consider X hat B1, the boundary steady state, the lower boundary steady state, what we can see that on the left side of this boundary steady state, it is not possible to find a feasible solution, a feasible control, so that we're able to increase the value of our sales level. So if we have a budget constraint, it's not possible to choose the control in a manner so that we can increase the sales level if the initial state value is small. And what we can also see here is we have two intersections. Obviously, if B would be small, then we would not have a single intersection, or in other words, it would not be possible to find a solution for which the state value increases. And but we will get to this later on. The important point that I just wanted to make here is that for initial state values, or for state values smaller than this X hat B1, it is not possible to choose the control in a feasible way so that we can increase the state value. So if you start here on the left side of the stalling equilibrium, the product is bound to fail. Not just because it's too expensive to advertise this product, it's just simply not possible. We don't have the possibility to choose the control in a manner that we can approach the higher steady state. If we compare that to the previously mentioned models in literature, when we consider there the X dot isocline and the critical level U bar, we see that in all those models, it is possible to choose the control in a manner so that we can increase the state value. So I mean, here we can basically see we just have the one intersection, the one larger intersection of the budget constraint with the isocline. We just have the highest boundary steady state. We don't have the lower boundary steady state. So in principle, for all these other models in the literature, it is possible to find a feasible control. I mean, of course, if the budget is too small for the gold model, it's also but it's different to our model where we have these two intersections. So the point that I want to make here is that if the budget is sufficiently large, it's possible for small initial state values to find a feasible control so that we are able to increase the state value, which is not the case in our model. So here you can see, even if you wanted to, you cannot find a feasible control that you can increase the state value. Here, this is the case only for the gold model. Here you can see that if the budget is too small, you are not able to find a control so that the state value will increase. But you do not have here this two intersection, this critical level for the control. So if the budget is too small, in this case, you have either, if the budget is too small, you will not have any intersection of the X dot isocline with this budget constraint. And therefore, if the budget is too small, you just are bound to fail. And and what this means also for the other products is that in principle, you are able to increase the state value. Sometimes it just might not pay off to do that. Okay, and when we have a closer look at this boundary steady state XB1, we also find that it has another interesting property, namely that it can be abnormal under certain conditions. And the conditions are those that you can find here. So yeah, in our paper, we prove these conditions. The idea here is to have a look at the Lagrange multiplier. And for a feasible boundary solution, the Lagrange multiplier must be non-negative. And this is only the case if either the steady state value of the co-state is larger or equal to 0, or if the solution is abnormal. And what we find is when we look at the steady state value for the co-state, we find that it only is positive under certain conditions, And yeah, if these conditions, the conditions on abnormality follow from the conditions for which it holds true that the boundary, the steady state value of the co-state is smaller than 0, and from that we derive these conditions for which the boundary steady state xb1 is abnormal. And yeah, what we can also show analytically is that for the largest steady state, the abnormal case cannot occur. So the negativity of the co-state for the second boundary steady state can be excluded. And yeah, we also know that yeah, we can also derive the stability properties of the steady states. We find that xb2 is a saddle point, the opacity is a saddle point, and yeah, depending on whether the lower steady state is a normal steady state or an abnormal steady state. If it's normal, then the xb1 is unstable. If it's abnormal, then it's saddle point stable. And this is something that I will show you here. If we have a budget constraint, we have even more possible outcomes. We have, as before, a Skiba outcome. We have what is now happening for our base case is this abnormal case where we have this boundary steady state, which is abnormal. And yeah, what could happen is also that we have weak Skiba just like before, but we make here a distinction between two cases, namely that either the steady state is at the bound, so we have the stalling property, and or that the steady states can all be in the, or the, yeah, that the separating threshold is in the interior of the feasible solution. And also what could happen is that the optimal solution is unique. But let us get now to the most interesting case, to the base case, where we find that the solution is abnormal. So what we can see here is, again, we have this x dot isocline, this U-shape, which gives us the level of the control above which, only above which we can increase our state value. What we will find, yeah, here you can see we have a solution path approaching the high steady state, a solution path approaching the low steady state. And here you can see that on the left side of the steady state, the control is at its upper bound. So you do as much as you can to prevent the decline of the sales levels. Yeah, but it doesn't help you. Yeah, just as said, you cannot do, because of the budget constraint, it's not possible to advertise so much that you actually can increase the sales level. And yeah, the number of users, the number of the sales level is falls because you cannot advertise enough so that it would actually increase and you would approach the lower steady state. And here, particularly at this boundary steady state, the boundary steady state xb1 is an abnormal one. As already indicated, it is a saddle point. So what you have here is this stable manifold, which leads to the boundary steady state. On the stable manifold, the control constraint is active. You would apply the maximum control efforts. And if you start on this stable manifold, you would get a solution path that fulfills all necessary optimality conditions from the maximum principle. So what you get here is a feasible solution path. You apply the maximum control that you can, and yeah, you would stay put in this boundary steady state, so to say, which itself is abnormal. And yeah, what you can see here again is when you take a closer look at the co-state values that you have for in vicinity of this abnormal steady state, you can see that the co-state values here get very large. Actually, they get infinite, and what it has to do is this property of the it has to do with the stalling equilibrium to the of this steady state. If you would have just a little bit more users, you would go to the higher steady state, which is much more profitable than the lower one, but you cannot go there because the budget constraint prevents it. You cannot choose the control in a manner that you can increase the state variable. You really want to do that, but you cannot do that. So what happens here is that the co-state gets infinite. Yeah, the closer you get to this stalling equilibrium. And yeah, you can see then here when you look at the objective, also here it makes a substantial difference on what on the objective value. And this is also the reason why this abnormal phenomenon occurs here. The co-state is infinite. This is something that the maximum principle does not want to. So you need to set the Lagrange the multiplier that you have in the objective to 0. And so this steady state that you have here is something peculiar. Anyways, you can see here that the objective value substantially differs depending on whether you approach the high or the low steady state. And yeah, this steep increase of the objective, it is, and this infinite value of the co-state variable is what actually leads to this abnormal results. Okay. Yeah, so yeah, then what we did, of course, is to have a closer look at how the outcome depends on the different parameter values. We had a look at parameter R, the discount rate. We had a look at what happens if the decision maker is more or less short-sighted, and we had a look at the forgetting rate. Yeah, here I just want to briefly, for time reasons, I don't want to go too much into detail now, but yeah, you can see here that if we increase the discount rate, what we arrive at is some weak Skiba solution where we have this boundary steady state. But in this case, if we increase R, we do not have this abnormal phenomenon anymore. The steady state is if R increases, this the co-state value at this boundary steady state gets larger to 0, and yeah, then it's just a conventional unstable steady state. And depending on where you start, you either approach the lower or the higher steady state. And if we look here, I have not plotted this figure. You have to trust me on this, but if you have a if you compare the objective value, the difference in the objective value for approaching the higher and the lower steady state, you can see here in this case, if the discount rate is higher, because you have less incentive to invest, the difference in approaching the higher steady state and the lower steady state is not as large as before, so it doesn't make such a big difference anymore. And yeah, the co-state values are not infinite anymore, and yeah, therefore here we have just a conventional weak Skiba case that we had in past models, plenty of. Yeah, and we can also have a Skiba case where some steady states are at the boundary steady state. So here you can see, yeah, the larger the discount rate, the further, yeah, the more attractive it gets again to approach the lower steady state. And yeah, you can have here an indifference point, so it doesn't make, yeah, you can choose between approaching either of the two solutions. We also did have a look at how the budget affects the optimal solution, and this is what I already indicated before. If you have a low budget, then it's not possible to choose the control in a manner that you can increase the state value at all. And this is the unique solution case that I showed you before. In case of no budget constraint, I mean, yeah. So what you would do is, if the budget is too small, you would just approach the lower steady state and make use of the little customers that you have. Advertising does not pay off. You do not have the budget to increase your customers. On the other hand, if the budget is large, then obviously the solution that you obtain does not differ from the solution you obtain without budget constraint. And for intermediate values of the budget, you have this abnormal weak Skiba solution structure that I just showed you. And if the budget decreases, what happens is that the larger boundary steady state moves to the left, the smaller boundary steady state moves to the right in the state space. And yeah, so they get closer to each other. And here again, the difference in approaching either the high or the low long run solution gets smaller and smaller. So what happens then is that abnormality does not play. So as the difference in approaching the different steady states is not so large anymore, it doesn't make too much difference in which steady state it approaches, and then you get a normal solution. And so what we also had a look at is how the particular shape of the budget constraint affects the results. And what we considered is some kind of self-financing constraint, meaning that you're only allowed to use up to a certain fraction of your revenues each time instant for advertising. And we also see here that this result with the abnormal steady state abnormality occurs also here. We have this phenomenon that we would like to a high steady state, but we cannot because the budget is not sufficiently large to be able to reach this high steady state. So also if we use a different budget constraint that you can see here, we obtain this result with an abnormal solution. And what I also had a look at is the case what happens if you have if the diffusion term looks a little bit different. So you don't so what is assumed here is that basically all customers are attracted by other customers, and this is sometimes makes sense, but it could also happen that some people start to use a product on their own, so they're so-called innovators and use the product because they think it's interesting. So if we add here a small parameter b, as long as it's not too large, then we also have this abnormal result. You can see that here in this phase portrait on the right, you can see here when we consider the x dot isocline that next to slightly to the left of the steady state, it's also not possible to find a feasible value of the control so that you can actually increase the sales level here. So so here also you get this abnormal solution in this case. Important is that this value of b is not too large. If it would be too large, then you would not have it. Okay, so what we saw in our problem is that this introduction of the network effect leads to a critical mass. So in the case without budget constraint, it's just you need some critical mass of customers. Otherwise, it's too expensive to be successful on the long run, so to say. In case of a budget constraint, you have a critical mass that prevents the increase of the customers, so to say. You would like to have it's just not possible. You do not have the capabilities to increase the sales. We see that the advertising policy, we saw how the optimal strategy depends on the different parameter values. We saw that we have a discontinuous advertising policy when the discount rate is large. So we had this Skiba policy where we had this jump in this advertising policy depending on which steady state you approach. This happens if we have a larger discount rate or a lower forgetfulness rate, we get a solution where the advertising policy is continuous. So the advertising budget leads to the existence of a stalling equilibrium, and the mechanism for that is, and the mechanism behind abnormality is that we would like to reach a more favorable outcome for us, a high steady state where we can make much revenues, but this is not possible. So this the budget constraint makes it impossible to reach the outcome that we want, and this is the mechanism that leads to an abnormal solution. This huge difference in the different long run outcomes, and in combination with the fact that you actually do not have the possibility to go to this higher steady state. And what we saw is what the model that we considered is a straightforward extension, a very simple extension of a model which is well known in literature. And what we saw here, that abnormality can happen in problems that can be nicely interpreted, and it's not just a sign of a bad model formulation. At least I hope so. Okay, so yeah, thank you for your attention.